Okay, hello everyone. Let's start our lecture for today, which is going to be on the topic of microstrip antenna. So microstrip antenna or simply patch antenna. This is a very useful antennas. But to start describing this antenna, perhaps uh, let's start from talking a little bit about transmission line. This is not the focus of this course, so I'm just going to go very briefly on microstrip transmission line. So instead of starting with microstrip antenna, I'm going to first start with microstrip transmission line. So and the reason that I'm starting with this is that you saw that when we discussed dipole antenna, we thought of dipole antenna as evolving from open-ended transmission line. When we talked about loop antenna, we thought of it as evolving from short-circuited transmission line. So it's very natural that when we talk about microstrip antenna, we think of microstrip transmission line first and then evolve that into the shape of the antenna that we want to study. So to start this, let me essentially start showing you a microstrip antenna that you see in my videos regarding lab. This is a microstrip antenna, and if you look at this portion of this, the very first portion, this is essentially a microstrip transmission line, and then later on it goes to this patch and this becomes our antenna. So it becomes wider as you see, and that's our antenna with certain geometrical dimension. But the beginning is essentially our transmission line. So similar to two-wire transmission line, this also has two conductors. One of the conductor you see, the other conductor in the back of the structure. So that's essentially would be one conductor or one PEC, perfect electric conductor, and the other one would be on the back. So this is extremely nice because this is a planar structure. So if you look at, for example, this, I don't know how good you can see it in the video, but the thickness of this is so small. So in the range of maybe just a few millimeter, maybe 1 point something millimeter, let's say 2 millimeter, and the rest is essentially just something to hold this for measurements as we needed to mount the antenna. But essentially this is extremely thin, and in the back of this you have your other conductor. So if I want to plot that, I'm looking at something like this, for example. So you essentially have one conductor here. So that's one conductor. This is very, in terms of thickness, this is very small. For example, let's say this could be maybe 17 micrometer, for example. And then you have a dielectric material. I mean, it could come in different relative permittivity or dielectric constant. For example, let's say 3, approximately 3. And then there is a thickness associated with that. So let's say T for thickness, maybe for one particular thing that I have in mind, maybe 1.52 millimeter. And then you have a small strip here, which is essentially the one that you were looking at right now. This one that you see here, that's essentially is this one that you see. You don't see the one that's in the back. And if you notice, there is a very thin layer here, not this black one. It's very hard to see, I think, in the video. And that's essentially this dielectric material. So if you have a situation like this, so essentially that becomes your transmission line. So this is now the other dimension. So this is the one that I'm using. Dash means it's a conductor. So it's going like that. So you see, essentially I have two conductors. I may call this perfect electric conductor or metal 1, and this is perfect electric conductor metal 2. So essentially you guide electromagnetic waves between these two, and here of course is air, and here you have a dielectric material. So essentially if you look at the electric fields that you're going to have in this situation, So you have things like this, and so, but the thing that to notice, the similarly here, that part of the electric field is in air, part of the electric field is in the substrate, but most of it is essentially concentrated in the substrate. So, but it's a bit different than a standard thing that we have in mind that, for example, electric field is only in the dielectric or only in the air. Here you essentially have two medium. And that's the reason that later on, we're going to talk about effective permittivity of the substrate. For example, right now the permittivity of the substrate is 3. And 3 means this material that I have, whatever it is, has a permittivity of 3. But if I talk about effective permittivity, then effective permittivity, maybe I call it epsilon r, effective would be less than 3. And the reason is it's going to be a combination of air and this 3. So if it was average, would be 1 plus 3, 4 divided by 2, 2. But average is not appropriate here because most of it is in 3. So it's going to be less than 3, but it's going to be very close to 3. That would be the effective permittivity of this transmission line. So essentially, we have electric field between these two. So, and that's going to guide the energy. And hopefully here, you're going to have your antenna essentially somewhere here. So let's say, let me just plot something here. And that would be a little bit wider than this. And this is becoming, and it also conductor. So it's a patch. So this essentially brings the energy from here and it goes to the patch. And this is the antenna that we discussed. So as you see, the first part is transmission line and then it's patch. So if you look at this, you see the similar structure. This is the transmission line that brings the energy. There is another thing between, which I'm going to talk later on, and then it goes to the antenna. So you give the energy from this point, and then it goes to the transmission line and here, and in the back you have a ground plane that essentially the electric field is uh, uh, its electric field are going to be closing on this ground plane. So this is something to keep in mind, and remember electric field is perpendicular to the PEC, so it's going to be perpendicular here. So now, just before continuing with this, maybe it could be a good idea that I show you a substrate. So for example, when you get a substrate, you get something like this. So if you look at this, this is a Rogers RO3003 substrate. So let me write it for you. It's Rogers, from Rogers Corporation, RO3003. That's the name of this substrate that I have. So this is one substrate that we have. So as you see, I have a copper layer on this side. On the other side, I also have a copper layer. So the thickness of the copper layer is very similar to this, 17 micrometers. So that's the thickness of that. And if you look at the between the two copper layers, that's the one that you have your dielectric material. And your dielectric material in terms of thickness is about 1.52 millimeter, and the permittivity is about 3. And so sometimes these dielectrics are a little bit lossy. They're not perfect dielectric. And then that's usually represented by loss tangent. So you look at the loss tangent of the material, then you would know your the amount of loss. So that's essentially the structure that you usually get. And now, for example, if you consider this PEC as this PEC, you can just keep that. So you can just, this can remain untouched. You can just keep that. And then if you want to create a transmission line, for the other side, you need to remove the part of the PEC that you don't need, and you only have the PEC with the certain width with the certain width that you want. So, and the one that remains essentially untouched, we could call it ground plane as well. So this is the ground plane, and this is the strip line that we have here. So that's for example about this. And just to tell you that these are called dielectric substrate. So let me write it here, substrate. And people do different things with these substrates. And for example, you can create different structures. And for example, this is the work of your TA. And as you see, there is a ground plane in the back, and in the top there are some square patches for a different purpose. So this is related to a different work. But you essentially see that you have lots of these type of things, and in some other applications you might decide to have these type of copper traces everywhere on both sides, not just one side. For example, if you look at this structure, so on this structure you have some copper traces, and also on the back you have copper traces. The other one that I showed you in the back was just a copper layer, but now you have traces on both sides. So these are not for microstrip antenna. These are just to show you that you can actually do different things with these dielectric substrates. So that's something about microstrip transmission line. So, but one thing that I'd like to mention here is that when you think of microstrip transmission line, you can also think of it as evolving from coaxial cable. For example, what is a coaxial cable? So you have a conductor here, you have another conductor here. So this is one conductor. So you can call it PEC maybe 2, and the inner one PEC1. And now if you start opening PEC2, what do you get? So you get your PEC1, and if you open this from here, you make it flat. This becomes essentially PEC2. And if you make this one flat too, like that, then this becomes your PEC1, which is essentially the structure of a microstrip transmission line. So you can think of microstrip transmission line to evolve from coaxial cable as a different type, because this is extremely nice. As you see, then you have a chance to fabricate it on flat structure. So you can integrate it with the rest of the circuit, which is a very nice thing, as opposed to having something that's not planar. So the integration of this would be extremely nice. So that's why this antenna has so many features that would be interesting in terms of integration with the rest of the circuit. And fabrication of that, you can essentially use a printed circuit board technology to fabricate that. And one thing that's important here, and I'm going to come back to this, is the characteristic impedance of transmission line. So we are thinking about 50 ohm characteristic impedance, and to control 50 ohm characteristic impedance for a given substrate. So if the substrate is fixed, for example, you are working with Rogers RO3003, you essentially play with this width to change the characteristic impedance, and in most of the time it's essentially 50 ohm. Now if I go back to this microstrip antenna, so this initial width that this antenna starts with, that's for 50 ohm at the frequency of operation of this. And you see the line gets thinner after that, right after that it gets thinner. That means now you're switching to a different characteristic impedance. So that's something to keep in mind. And the line becomes thinner. That essentially means you're going to a higher characteristic impedance. So it starts from 50 ohm and it goes to a higher characteristic impedance later on, and then it goes to the actual antenna. So that's a little bit of explanation for this patch antenna. So this is, please keep this in mind. And then we now go to our patch antenna to see how it works. Before going that, I just remember that we were dealing with the transverse electromagnetic mode, TEM mode, in this coaxial cable. So equivalently, we have a similar thing, but remember now we have two different mediums here. So the mode for this that we are concerned with in this course is called quasi-TEM. So I'm not going to get into details of that unless I need that, but this is the mode would be quasi-TEM, the fundamental mode that we have in this case. So now let's go to our antenna. But before going to the antenna, let me also mention something else. The reason that these transmission lines are not radiating is that we have this current cancellation. And when you go to your A, which is the integration, and in the integration you have J's multiplied by some other things, these J's cancel the effect of each other, one this way, the other this way, so you don't get your essentially radiation from this transmission line. So if you think of this as some evolutionary form of coaxial cable, you can conclude the same thing, that the current here is going to cancel the current on PEC number two when you calculate the radiation from that. So essentially this is not a good radiator. So it's maybe it's not complete cancellation, but it's still, because these are extremely close, in this case 1.52 millimeter. So then you may say, okay, they essentially, I have my cancellation, and this is not going to radiate the same way that, for example, two wire transmission line does not radiate. I have this situation. Now let's see what's happening at the patch that make the patch antenna able to radiate. So to study this, perhaps it's good that we start from a coordinate system. So let me have this as X, let me have this as Y, and let me have this as Z. So I have my X and Y and Z. So this is the situation that I have. And when I'm looking at that, so Z would be the direction that my guided waves are going to travel, and this is my X and Y. So now imagine you have a patch, and this patch, the width is W and the length is L. So that's my patch. And also remember that this W cannot be very small, because if it becomes a small, you essentially get to the transmission line, and you're gonna be you're not gonna have a good radiator. So we're gonna talk about what should be W, but just remember it cannot be too small, otherwise you would have your transmission line. And now for now, let's assume L is half a wavelength. And later on, you see that L is in fact approximately half a wavelength, but for now, we just assume it's half a wavelength. So if it's half a wavelength, what's unique about half a wavelength that makes it an interesting structure? So to explain that, perhaps it's good that we see it from a cross section. So let's study that from, so if this is my X, this is my Z, let's study that in the XZ plane. So let's consider the antenna in the XZ plane. So you have a PEC ground plane. So this is essentially this side that I'm plotting right now. And then you have your dielectric substrate. I usually write epsilon R to say it's a dielectric substrate. And then you have your patch, but then I'm in the XZ plane, so X and Z plane. So this is essentially would be L, which is approximately half a wavelength. So what I'm showing here would be this with this right now in the cross section. So that's what I have. So this is what I'm showing here, L equal half a wavelength. Now, if I go to my patch antenna here, this is again my transmission line, this is my patch. It is almost like saying, let's look at the antenna from this cross section. So if you look at the antenna from this cross section, you see only this side of the patch, which correspond to this side. So that would be what you see, and then you also see a ground plane. So that's what I have. So instead of looking at this antenna from top view, we're going to look at it from side view. So that's would be what you see. So this is L half a wavelength. Now assume that I'll do my job correctly and I can give power to this antenna, because this is very important to be able to give power. Remember, if the loop antenna, if the dipole antenna was one complete wavelength, things were okay with the dipole antenna in terms of being complete wavelengths. The problem is the energy is going to reflect back completely here. So almost completely here. So the problem here is that you cannot give the energy. So we need to make sure that we can give the energy to the system. But let's assume we give the energy to the system. So then the energy comes to the patch. And now what's going to happen? So what's going to happen is that now you have two conductors, one conductor in the top, one conductor in the bottom, and you have now current in the system. So now at this point, you may start analyzing microstrip antenna from different viewpoint. The simplest one, which to some extent, in my opinion, is the most intuitive one, but it has its own limitation. It's the simplest one anyways. It's a transmission line model. So as soon as I say transmission line model, that means you're going to look at this structure from transmission line point of view. You would say, I have two conductors, and these two conductors form a transmission line. Why it's transmission line? Because this thickness is so small. By definition, these dielectric substrates are so thin. So this is a transmission line. So that part is okay. And then you look at the end of this transmission line. For example, let's assume this point is A, this point is A prime, this point is B, this point is B prime. So if you look at the end of this transmission line, this is essentially open circuit. So I can, because these two are not connected together, this is open circuit and this is also open circuit. So this is the situation that I have. So from the transmission line point of view, it's like having two wires and you've actually induced energy in the system, and then here is open circuit, here is open circuit. And now the question is, what is, for example, your current distribution in a situation like this? So it's, of course, at open circuit, we expect zero current, and then it is about half a wavelength. So your current is very clear. So it's zero here, and then half a wavelength, again, go back to zero. So essentially, you're going to have half of a cosine. So if I want to plot the current distribution here, I'm going to essentially have this current distribution. So this is my current distribution going to zero here, going to zero here, and going to max here. Again, remember, this is not exact. This is based on assuming that this is a transmission line. So this is my current situation. And again, remember that I still have my current cancellation because of the top PEC and top and the bottom PEC. So if the current in the opposite direction, they cancel the effect of each other. So this is my current. And if I look at the current, I cannot really understand what's going on if I have any effect that can result in radiation for me. So now we're going to go and ask ourselves, what would be the essentially voltage distribution in this transmission line? So remember, we modeled it with the transmission line. So if you have open circuit here, so let me remove the current here. So the current, we know it was zero. So now if I have voltage, so at the open circuit, my voltage would be maximum, for example, this. And again, half a wavelength, it becomes again maximum with a different polarity. And this is, remember, this is also half a wavelength. So this is my voltage distribution. So you start with maximum at open circuit, and you go again to maximum with a different polarity. And at the center, you're crossing zero voltage. So that's what we're gonna have. So remember, this is a cosine, one wavelength. So for the current, because it goes from 0 to 0, we chose this part. But then for the voltage, because it goes from max to max, we are choosing this part of the curve, this is still half a wavelength. So that's essentially the curve that we have right here. So if I go again plot one of these, so remember I was in XZ. So again, I'm essentially in the same XZ. This is the bottom PEC. I have my dielectric substrate. I mean, this is of course not to a scale. This is could be 17 micrometer. This is 1.5 millimeter, for example. I have my epsilon R, and again, I have, this is the length of the patch from here to here. So this is essentially point A, and this is point B. This is the one that I'm plotting. And if you come here, this is your A prime that I'm showing, and this is point B prime. So these are the point that we are talking about. So if that's the case, now if it's half a wavelength, then for example here, I can have maximum voltage, and then I can go to 0, and then again, I'll arrive at the maximum voltage. So again, this is point A, this is point B, this is A prime, this is B prime. So this is my voltage. Now let's continue with voltage discussion. So if this is my voltage, that essentially means I have maximum voltage at my open circuit, and therefore you're gonna get very strong electric field between these two. So that would be lots of electric field here. So I'm showing it very dense. And as you go to the center, the number of electric field gets sparser. And then after that, the polarity will change. And it still is very sparse in the beginning because voltage is not too much. And at the end, it becomes very heavy. So you see the voltage on this side is result in electric field in this direction. On this side results in electric field in this direction, and that should be understandable for you because positive voltage means plus here, minus here, and this would be the direction of your electric field. So that's the situation that I have. But also remember that because this is a finite side, you're gonna also have fringing effect. So you're gonna have situation like this as well. So, and this would be this. So that's my fringing effect. And remember, electric field is going to be perpendicular to both PEC. So that's my fringing effect that I have, like, for example, capacitor that you learn from your circuit. And if you look at the direction of this electric field, you actually see again cancellation effect, because if you, I can just plot them here. So here, these are very strong. Here I have these, and then you have your fringing effect in the same direction, similar to this. So now if you look at this part and this part, you see that your electric field also, they're going to be opposite to each other. And that makes sense because remember, this is half a wavelength. If you go half a wavelength away, everything is gonna reverse. So far this is our observation. But then if you start looking from the top, so if you start looking from the top, from here, if you start looking from here to the system, then you see something very interesting about this fringing effect. Look at this fringing effect here. So this is my arrow, it goes up, and here it's like that. And now look at this fringing effect. It comes like this, but here it's like this, to be continued like that. So although you see fringing effect in the opposite direction, because you are looking from this plane, but as soon as you look from the top, these two vectors here, if you look from the top, they become actually same direction, because this, the continuation of this is this, the continuation of this is this. So now, if you look from the top, you see this, and you see this, which are in the same direction, and I plot them here, right here. So you get actually two electric fields from the top that they become in the same direction. So let me try to represent that in 3D picture here. So essentially you're gonna have things like this. If I can do that, I'm not sure if I can do that properly, but let me try. So this is this fringing effect, and on the other side you have a similar situation like this. So you have a similar situation like this. Now let's look from the top. If you look from the top, then what do you see? So if we look from the top, and what would be the plane? If we look from the top from here, what we see essentially would be ZY plane. So I'm just gonna have Z and Y plane. And what I'm gonna see would be, I'm gonna see this L, and this is the other one is my W. So this is my patch. And remember, my L was approximately half a wavelength. I assumed it was exactly half a wavelength in my discussion. And now look at this part. So because now you're looking from the top, you only see this part of the fringing effect. These parts are vertical, you don't see them. So all of these goes this way. So when they go this way, essentially they become these. So essentially I have these going this way, so these are that. And then I have these going this way, so, and these are, would be shown here. Like this. So now you see that your patch from the top is like having creating some in phase electric field. So you have a set of electric fields on this side, you have a set of electric field on this side that they become in phase. And this is very similar to the concept of dipole antenna, that in dipole antenna you get two in phase electric current. Now, in this case, you're going to get two sets of in-phase electric field. So, I mean, maybe we can also convert them to something else in terms of current, but that's for the future. But just look at that as two sets of in-phase electric currents. Whatever this does as well. So we call it in phase. And here we have the same situation, that we have two sets of in-phase electric field. So they're going to create, these are the ones that, according to this transmission line model, are responsible for creating radiation from this antenna. And based on that, you can even understand the polarization that's coming from this patch antenna, because you have these electric fields in phase here, this electric field in phase here, then this would be essentially polarization. It's linearly polarized, and it's going to be in this direction, in the direction of these electric fields. So that's essentially one way of looking at our patch antenna. So this now that we understood this, we need to look at another aspect of patch antenna. Okay, so let us now start with a little bit of design of microstrip antenna. So if you want to design microstrip antenna, remember the first part is transmission line. So essentially, if we are looking at this part, this is our transmission line, and we assume that it's already been designed to have, let's say, 50 ohms. So if you fix your dielectric substrate, then you're going to have an appropriate width of this strip line to have proper 50 ohms. So essentially, you end up with designing the patch, and for designing of the patch, you have two unknowns. So, and the unknowns, I can just write it here. The unknowns that you have is the length of the patch and width of the patch. So let me write unknowns L and W. These are the things that we don't know. So if we know their dimension, we can have this patch on the substrate, and then we have our patch. So the other thing, now what we know, so let's call it known, is the frequency at which we want to design this antenna. So let me call this FR, and R stands for resonance because that's a narrow band antenna in the format that we have it. So I call it FR, resonance frequency of the antenna. So if I give you a frequency, and then I can ask you for L and W, and that would be finding the geometrical distribution of your patch. This is your L, this is W. Of course, I'm assuming that I'm dealing with rectangular patches here. Patch could have different shapes, but we're not considering it here. For example, it could have a circular shape. But the one that it is our focus is the L and W. So if I bring now this patch antenna again, so essentially I'm looking for the dimension of this rectangle, which is my patch. So I want to know the length and the widths in this direction. So that's my focus. So now when it comes to widths W, so this width W, which would be, if I make this a little bit cleaner here, so this is my width, of course. So this width can affect things like impedance, bandwidths, and so on. So, but the focus here is that having a width that results in good radiation efficiency. And if that's your purpose, you can immediately find W to have a good radiation efficiency for your patch antenna. So in this course, this would be the equation that we're using for the widths of the patch. So the widths of the patch, the equation that we're going to use to get it would be 1 divided by 2 FR mu naught epsilon naught a square root of 2 epsilon r plus 1. So this would be the equation that we have. And remember that 1 divided by a square root of mu naught epsilon naught is essentially the velocity of light in free space. So you may also write this equation as, so 1 divided by that would be C naught, and this naught means you are in free space, air, and then you get C naught divided by 2 FR. So that's what you have, and then you get 2 divided by epsilon r plus 1. And if you look at this equation, C naught, we already know it's approximately 10 to the power of 8 meter per second. FR is the frequency at which you're designing. For example, this microstrip antenna that I'm showing to you, this is close to 10 gigahertz. So the FR for this is about 10 gigahertz. And then epsilon r is the permittivity of the substrate. For example, this substrate that we had here, what I discussed was about epsilon r equal 3. So that would be the epsilon r of the substrate. Remember, I also talked about effective permittivity in the beginning of the lecture. This epsilon r is not effective permittivity. It is directly the permittivity of the substrate. Whatever the substrate is, that would be that. So this equation results in a patch antenna with good radiation efficiency. So if I give you FR, and if you know your substrate, so in terms of known, maybe I should add, we also assume that we know our substrate. So then if you know your substrate, you know epsilon r, therefore you're essentially done. So let's have an example here. And the example that we have would be the following example. So let me, for example, remove this. And I assume that I have a substrate, which is RT toroid 5880. This is the substrate that I'm using in this example. And for this substrate, I have epsilon r of the substrate is 2.2, relative permittivity is 2.2, and the thickness H is 0.15 88 centimeters. So remember in the beginning I said T for thickness. Here I'm using H to be consistent with the note. So H, or height, is essentially the thickness of the substrate. So this is about 1.6 millimeter or 0.1588 centimeter. Now these are my substrate, and I'm also saying I want frequency of 10 gigahertz, which is the center frequency of X band. So this is my FR. Now I can go here and I can find my W. So W becomes C naught 3 10 to the power of 8 meter per second divided by 2 times F, which is 2 times 10 to the power 10 times 10 to the power of 9. So that would be my 10 gigahertz. And then I'm going to have 2 divided by epsilon r plus 1. And my epsilon r of the substrate is 2.2 plus 1. So if I find that, that's going to be about 1.186 centimeter. So that would be the approximate value for the patch. Let me check that if I have everything correctly. Seems I have it. So it's 1.186 centimeter. That would be the width of the patch. So you see, with knowing substrate and resonance frequency or operational frequency, immediately you calculate W. Just to emphasize, this epsilon r is the epsilon r of the substrate. So that becomes your W. Now let's see what would be the other step, which this is a standard. The other step would be essentially finding L. So to give me a little bit more space here, let me remove this picture from here, and perhaps I can just show it from the top view. So this would be the top view, and this would be my W here. This would be my L, and I'm gonna feed it from this side. So this is the W and L, and instead of that, maybe I can just use a microstrip line. I'm gonna talk about feeding later on. So this is the situation that I have. Now I need to go for my L, which is the length of the patch. Now at this point you might say, Puyan, that should be easy because L is half a wavelength. So if we do something like that, then we say, okay, what is wavelength? Wavelength is velocity of light divided by F. And this is my F divided by 2. But then there is a problem here, because this wavelength, what is this wavelength? Is it the wavelength in air or free space, which then correspond to C naught, or is it the wavelengths in the substrate? The wavelengths in the substrate would be velocity in the substrate divided by that. So instead of C naught, you have the velocity in the substrate, and velocity in the substrate would be smaller than velocity in air. So it would be C naught divided by a square root of epsilon r divided by FR. So you see, lambda in substrate is going to be smaller than lambda in free space. So you need to be careful. You need to be able to distinguish between them, that which one is the C that, I mean, which C you're going to use. Are you going to use C naught, which is C in air, or C in the substrate? Which one you're going to use? If you use C substrate, you end up with C naught divided by a square root of epsilon r as for the velocity of light. So, but the answer is essentially none of them, because if you have a microstrip, this is one conductor, this is the substrate, this is the other one, you're gonna have some field in air, and you're going to have some field in the substrate. The thing is, the fields in the substrates are more, so it's more in the substrate. So essentially, I need to define an epsilon r effective, and then instead of this lambda here, I can maybe write it lambda effective, and then I can change that to C effective, and then I'm going to change that to epsilon R effective. So this is what I need to do. So I need to have the concept of epsilon R effective, which is going to be close to the epsilon R of the substrate, because most of the feed lines are in the substrate, but still we need to have an expression for that to get to the effective wavelengths that we have. So the next step for us would be to have the expression for epsilon R effective, and I'm just going to write that here. So let me write epsilon R effective. Epsilon R effective becomes epsilon R plus 1 divided by 2. So this term is very obvious, is like epsilon R of the substrate plus 1, which is epsilon R of air, divided by 2. So that's an algebraic average. But there is more term here, epsilon R minus 1 divided by 2. And then you get 1 plus 12H divided by W minus half. So this would be the equation for epsilon R effective. So let me check that again. Okay, so this is our equation that we have. And this is nice because it follows the previous equation directly. So previous equation, let me write the previous equation here. W was C naught 2FR 2 epsilon R plus 1. This was the previous equation. So in the previous equation, of course, I didn't have epsilon R effective because I haven't found it yet. So this equation was based merely on epsilon R, and that's why I used 2.2. But after this equation is done, now I have access to my W. So this W is also known, and H is the height of the substrate or thickness of the substrate, which I also have it here. And then epsilon R is the epsilon R of the substrate 2.2. So I can start plugging here. H would be here. W, I just found it. It's here. Just be careful about the dimension. This is now centimeter. This is also centimeter. So that's fine. They cancel each other. And you start plugging 2.2 to get your epsilon R effective. Now, if we get that, you need to also check your answer. So epsilon R effective would be close to the actual epsilon R, but a little bit smaller. So let's see what's going to be the value for this example. So if I have the calculation here, which I do, if I start plugging, maybe I can just plugging and then just to make sure that you understand it, 2.2 plus 1 divided by 2 plus 2.2 minus 1 divided by 2, 1 plus 12H, and H is 1588 divided by W 1.186 to the power of minus half, and that's gonna give me about 1.972, which I'm gonna write it here. So you see, I started with a 2.2 permittivity, but I ended up with 1.9. So it's still closer to 2.2 than 1, which is air, but a little bit smaller because of the effect of the air. So now this is my epsilon R effective. That sort of encapsulate the effect of air and the dielectric substrate. So that's about this one. Now, if we have that, you might be saying, okay, now it's easy. So then I can just say L is half a wavelength, as we discussed in the beginning of the lecture. And this time L is C naught, but it's not C naught because it's not in the air. So velocity of light would be smaller. And to make it correct, you say, okay, epsilon R effective, and then divided by 2. So if you do it like that, still there is a problem here. So this is very good because you are saying half a wavelength and you are careful about your wavelengths, you're considering the effective permittivity, but still there is a problem with that. The problem is when you have the fringing effect. So remember, fringing effect, we essentially had a situation like this with the fringing effect, that we had some extension of electric field. These are the fringing effect for us. So we had this. So from the perspective of electromagnetic waves, the actual length of the microstrip is this L plus this extension. You see, this is, I call it delta L to be consistent with the textbook, delta L. So essentially from the perspective of EM waves, the total length that I have here is L, the actual thing that you fabricate, plus delta L plus delta L. So this is the length from the perspective of EM, and this is the length that we fabricate. And of course, we are interested in the length that we need to fabricate. So half a wavelength is correct. We need to be half a wavelength. And which wavelengths? Of course, so I should have had an F here. So C naught divided by F. So this is my FR here. So half a wavelength is velocity in the effective material divided by F. That's wavelengths divided by 2. So this is correct. But this side is not correct. This side should be, instead of L, this side should be L plus 2 delta L. Because I know that what matters is this L and these two small delta L that I have. So I say L plus 2 delta L should be equal to that. So now you might say, okay, what is delta L then? And that would be another equation that we have to write the equation for delta L. So let's write the equation for delta L. So the equation for delta L becomes this equation. Delta L becomes 0.412 H, 0.412 H, and you already know H is the thickness of the substrate or height of the substrate. And then you have a fraction. And in the fraction, you have epsilon R effective that we just found, 1.972 plus 0.3. And then you have W divided by H plus 0.264. And then here you have your, again, epsilon R effective minus 0.258. And then you have WH plus 0.8. So this is the situation that we have. Let me double check that. This side is 0.412 H. H is the thickness of the substrate. The first factor is epsilon R effective plus 0.3. This is epsilon R. This factor here is epsilon R effective minus 258. You have that too. And then the second factor on both numerator and denominator depends on W that we also found is here. So one of them is WH plus 0.264 and then WH 0.8. So that's my WL. Now, for the example that we had, let me see if I have my calculation of delta L. I hopefully have it. Yes, I have it here. And if you start plugging all these things that we have, you can check the notes, and delta L becomes 0.081 centimeter. So you see, it becomes almost 0.8 millimeter. So a little bit of extension. And you might say, oh, this is very little. But remember, everything is with respect to wavelengths. But and still we should count it. So delta L becomes 0.081 centimeter. Now, this is our delta L. Now that we know our delta L, we can find the lengths that we actually need to fabricate, because this was the length from the perspective of waves is L plus 2 delta L, but the one that you fabricate is from here to here, which is this L. So we know that L plus 2 delta L should be half a wavelength, where wavelengths is effective wavelengths, which is equal to that. Therefore, now you can find your L, and your L becomes half a wavelength, but effective, which would be C naught divided by FR, C naught divided by 2FR epsilon R effective and then minus 2 delta L. That's because L plus 2 delta L then becomes half a wavelength effective. So if we have that, now let me see what would be the value if you start plugging here. So C naught is 3 10 to the power of 8, then 2 FR is 10 times 10 gigahertz, then epsilon R effective, we have it at 1.972. So that's, and minus 2 delta L. So my delta L is right there. So it is 0.081, because this is velocity is meter per second. So I need to write this in meter too. That's right now in centimeter. So 10 to the power of minus 2 to convert it to meter. And that's going to give me 0.906 centimeter. So this would be the, so essentially about 9 millimeter, 0.906 centimeter. And that would be the length that I have. So now to summarize what happened here is that essentially I'm going to use 4 steps in the design of the geometrical situation. So again, remember that I know my substrate, therefore I know my epsilon R, and I know my H, height of the substrate or thickness of the substrate. You know what frequency you want to design for, and then you know you want to find your L and W, which is, this is your L and this is W, and the feed is coming this way. And there are other ways of feeding this that are going to be discussed in the next lecture. So to start, this is the first equation. So the first equation is to use this equation to have a good radiation efficiency, and this only uses epsilon R of the substrate. It's not effective, just simply epsilon R of the substrate. That's your first equation. After you're done with this, you know your W. Now, the next step, you go and find epsilon R effective. So to have your epsilon R effective, you need to know the epsilon R of the substrate, you need to know the H of the substrate that you know, and you need to know the width, but width you already found it from here. So you just substitute it and you find epsilon R effective. That's your second step. Now, the third step, you go and find the extension of the length. So this is a step 3. For the extension of the length, you need to know your W, which you found it in the first step, and you need to know your epsilon R effective that you found it in the second step. And then you have everything, you can find the extension of length. So that's your step 3. And after that, this is your step 4 that relies on knowing epsilon R effective that we have, and also the extension of the length. And at the end, you have the value for L, 0.906. So your L becomes 0.906 centimeter, and your W in this case is 1.186 centimeter. So that's essentially the end of our design. Now, when you simulate it, for example, in the commercial simulation software, you may still need to tune it based on different things that you're going to see it in the simulation lab. So I hope it's clear for you. So remember, we have 4 important steps when it comes to the geometrical design of our rectangular patch. Thank you very much.